Thank you. Thanks, Lori, for the introduction. It's a great honor today to introduce our first speaker, my graduate advisor, Professor Rich Sakely. Professor Sakely has been a professor here, part of the chemistry department for over 40 years, where he and his research group have really been pioneers in studying the nature of water, from chemical bonding interactions between single water molecules to the properties and the structure of liquid water and water surfaces. But beyond his research, Rich is maybe best known for his unmatched enthusiasm when it comes to communicating science and inspiring the same in his colleagues, his collaborators, and his students. So without further ado, please join me in welcoming Professor Sakely.
Thank you. It works. Shocked. So first off, thank you very much for inviting me. This is a great honor in almost all ways. The reason I was invited has as much to do with the fact that somebody told Lori that I play guitar and can lead singing as it does to do with whatever science I've done. So this is, let's talk about the music aspect of this, okay? So first of all, show me your hands if you are a high school student, please. I want to keep track. You're our honored guests, and this is really directed at you, okay? So how many of you saw this movie, The Way of Water, Avatar? One of the most expensive movies ever, The Way of Water, so we kind of have that theme adopted here. So leading up to a little bit of a musical introduction for those of you who are watching this from faraway places in Europe and all over the US, you may or may not understand that California has a reputation as being the land of perpetual crisis, going back many years. These are some recent headlines from the land of perpetual crisis. California battered by rain, floods, and blizzards. This is very recent. Snowmageddon. I'm a skier. My family we have a cabin up in Lake Tahoe, and you can see some pictures of what's going on in Lake Tahoe right now. They're calling this Snowmageddon. California declares emergency in counties buried by snow as the latest storm moves in. Our condo is so buried in snow you can't see out of the second story windows. On the other end of the spectrum, a little earlier in the month, we read this: water crisis in the West. Massive reservoir, Lake Powell, hits historic low water levels. The two main reservoirs that supply water to California and the Southwest are very empty. So this is the other end of the spectrum, the serious drought going on there. And that impacts California. Southern California gets a lot of its water through the Colorado River that is diverted into Los Angeles area, et cetera. So here's the other end of the spectrum. Columbia University, this is very recent, Columbia University scientists are predicting record-breaking heat will return this summer. Now, all these headlines are like within the last week or so. Here's from Europe. I don't want to leave Europe. Europe is very much involved in this crisis stuff. Here is a French drought alert after the driest winter since 1959. I think this is 3 days old or something. Water sobriety crop switching in Italy and France as they brace for another year of drought. And this Europe braces for severe drought amid winter heat wave. So you're seeing these, the bottom line here is extreme fluctuations in weather. Between drought and floods, it's going back and forth. And I was asked to sing a water song. And the first thing I told Lori and others who told me, and Omar, I can't sing. I can play a guitar, but I can't sing. So I recruited a couple of people who can sing. This is Charlie and Alex, who will help a lot with the singing. But I wanted to pick a good water song, and as you can see, I'm old. So there's a bit of a generation gap with you. I think you high school people, your parents or maybe your grandparents knew about the Creedence Clearwater Revival years. Raise your hand if everybody, who has heard of Creedence Clearwater? See, my age is showing. This is a local band. They're from El Cerrito, California, which is 13 miles away from here. And they had a big impact back in the 60s and early 70s, led by John Fogerty. And they had these two rain songs were in top 10 during their years. So we can choose between Have You Ever Seen the Rain and Who'll Stop the Rain, these two extreme streams of the California water crisis and now happening in Europe. We decided it was more important to do Have You Ever Seen the Rain, because the snow's going to melt and we're going to go right back to the big drought. So Charlie, Alex, come on up, and we're going to play Have You Ever Seen the Rain for you. And you all have to sing. Raise your hand if you know the words to this. We passed. Omar, you've got to come up here and sing with us. Okay? Enthusiasm and patience. We have to turn this on. 1, 2, 1, 2. Check.
Check one.
Is that good?
1, 2. Let's see if that's loud enough for you.
Check, check.
Yeah, cool.
Hi, Mom.
Hi, Mom.
Hi, Mom.
Shall we? Everybody's going to sing, right? Ready? 1, 2, 3.
Someone told me long ago, there's a calm before the storm. I know it's been coming for some time, and it's over, so they say. It'll rain a sunny day. I know, shining down like water. I want to know, have you ever seen the rain? I want to know, have you ever seen the rain? Coming down on a sunny day. Yesterday and days before, sun is cold and rain is hard. I know, been that way for all my time. When the never-ending goes through the circle fast and slow, I know it can't stop. I wonder, I want to know, have you ever seen the rain? I want to know, have you ever seen the rain? Coming down on a sunny day. Yeah, I want to know, have you ever seen the rain? I want to know, have you ever seen the rain? coming down on a sunny day. Thank you.
Singers. So for you in Europe, that's hoping that you get rid of the drought problem. Credence somewhere in the world is on your side. Okay. Shall we do some science, or shall we do another song? Okay, so along the subject of the way of water, I'm going to talk very briefly about an aspect of water that's really impacting the world, as our songs alluded to. Oh, something happened here. Okay, hopefully this is going to work. I'm going to talk about some of the work in my research group on probing complex aqueous interfaces. And the aqueous interface of central interest right now, I gotta see this, is this one here, the carbon dioxide chemistry that's occurring at the surface of the oceans. So we all know that the oceans comprise 2/3 of the surface area of Earth, and to a crude approximation, oceans comprise about 0.5 molar sodium chloride. And here what happens as diagrammed, carbon dioxide in the atmosphere dissolves in the surface layers of the ocean and goes to dissolved carbon dioxide, as shown here. And that dissolved carbon dioxide hydrolyzes in the surface area of water and makes carbonic acid. Carbonic acid has a pretty short lifetime in room temperature water, about 20 milliseconds. And carbonic acid undergoes proton dissociation to bicarbonate and a proton. And the bicarbonate loses its other proton and forms carbonate. And all that happens, and then carbonate reacts with the calcium and magnesium that's present in the oceans to form limestone. This is the essence of the Earth's carbon cycle. And it's fluctuations in this that are causing us all this chaos in the weather. There's way too much carbon dioxide in the air. That causes global warming, and as the Earth warms, more water evaporates primarily from the oceans. There's more water vapor in the atmosphere. That atmospheric water vapor condenses out on atmospheric aerosols, makes rain. That's very exothermic, and this creates winds and all sorts of the complications that we're dealing with now. So it's very crucial to understand all the details of this carbon cycle. And many details remain to be understood. And so I'm going to talk about the work in my group to understand this. There's lots of groups around the world working on this, both theoretically and experimentally. My apologies if I don't talk about it, but you did not agree to sing, so. And by the way, as for tomorrow, much of this same chemistry is operative in our bodies and in the bodies of mammals in general that holds the pH balance. That's also a carbonate based problem. So understanding the chemistry of these systems, particularly the chemistry that happens at interfaces between water and membranes in biology, or water and air in the case of the oceans, is crucial. Okay? Before we can understand the chemistry of the surface, we need to understand the chemistry of water all by itself. And as was alluded to, there's much to be learned about pure water yet. This is a quote from a very famous scientist, Willis Robinson, in his book on liquid water in 1997. He concludes the chapter, "Liquid water remains therefore the most important unsolved problem in science." This is a quote from Mark Twain, another famous San Francisco personality. "Whiskey is for drinking, water is for fighting over," and this is very true. If you could look at me close up, you'd see bruises and bumps all over my body from giving talks about our water stuff at water conferences. It's ferocious arguments happening. For example, this water's the most important problem in science. I quoted this in a National Science Foundation proposal that I wrote 10 years ago after being funded for many years to do the work. One of the reviewers said, "Seikle doesn't understand theory. Everything's known about water. This is a waste of money." So water is for fighting over. And here, one of the most famous current writers who writes about water is Philip Ball. He has 2 books on water, which I strongly encourage you to have a look at. And he says in this is his earlier book, he says, "Yet another theory of liquid water structure raises questions about interdisciplinary design, astrobiology, and all of this. Water, an enduring mystery. It's a constant battleground." What's the problem? Why don't we understand water? I remember years ago when my mother was in her 90s, I came home from Berkeley to visit in northern Wisconsin, where I come from, and my mother would say, "Are you still doing that research stuff?" I'd say, "Yes, Mother, I'm still doing research." She said, "Are you still working on water?" I said, "Yes, Mother, we still do." She said, "What can you not know about water?" So that's kind of a general feeling. So we understand everything, quote unquote, that there is to know about an isolated water molecule. We know its structure, its dipole moment, its quadrupole, to many decimal places. Fair to say we know everything about an isolated water molecule. But remarkably, what we still can't properly describe in quantitative detail, until extremely recently actually, is how 2 water molecules touch. And this is crucial because theoreticians have shown us that the cohesive energy of water, the forces that hold liquid water together, et cetera, are dominated by what we call pairwise interactions. That is, water molecules interacting 2 at a time. And that's embodied in the physics of this water dimer. So my feeling is if your model of water, of which there are probably 100, can't describe the water dimer in significant detail, your predictions, especially when you go out of usual so-called STP conditions, are questionable. Theoreticians don't want to hear that. That remark gets me in trouble all the time. But very recently, this problem has been addressed. My group has measured lots and lots of spectra in the terahertz region of these clusters and so on. If you want to address this question of what the structure of the water dimer is and the trimer and all of that, so we can get these details, you need new tools. I consider myself and my research group at Berkeley to be tool makers. We make new tools for things like this. So I want to tell you just a little bit about our work toward a universal first principles model of water from terahertz spectroscopy of water clusters, as I have alluded to, and theoretical calculations. Many groups have worked on the theoretical calculations aspect of this, and quite a few groups are also extracting detailed microwave spectroscopy in terahertz. So this is in German. One of my brilliant graduate students was a German guy, Frank Keutsch, and this is his slide. But we want to build up the liquid, our understanding of the liquid, one molecule at a time. We want to understand every detail about the water dimer, the water trimer, tetramer, pentamer, hexamer. We're up to octamer now. We want to understand every detail of this from terahertz laser spectroscopy combined with state-of-the-art theory. So my group has probably published 100 papers on this subject. Many people have worked on this. This is the state-of-the-art. We now have reached a point where there is what I would dare to say is a perfect understanding of the water dimer in a theoretical model. This comes from this brilliant guy, Francesco Paesani at the University of California, San Diego. He has put together this beautiful model with help from Claude Leforestier, so you understand all these details of the water dimer. So I think it's fair to say the pairwise interactions of liquid water are now quantitatively understood. The pairwise interactions comprise about 80% of the cohesive energy of liquid water. 15% is in in the form of three-body interactions. Those are embodied in the water trimer, and that's quite far along as well. The rest is four-body, five-body, et cetera, that are much more complicated. Okay, so that's the base. That's what's going on pure water. Now what I want to talk about is the interface of water. In this case, we're talking about the ocean, so it's the interface of the oceans with air. How's my time? I lost track.
I'll let you know, but you're fine.
So the new tool that we want to use to look at aqueous interfaces, first of all, is what we call fast flow liquid microjet mixing system. This is building on work that was done by Manfred Faubel in Germany, who I had the pleasure of spending a sabbatical with and borrowed a lot of his ideas over the years. So here, the idea, as I said, the lifetime of carbonic acid is about 26 milliseconds, and it will decompose into water and carbon dioxide. But with a fast mixing system, we can mix hydrochloric acid with carbonic acid, with sodium carbonate, and we can then generate carbonic acid in whatever amounts we want. And with a fast mixing system that has a mixing time of half a millisecond. So we can study the carbonic acid that's produced. So over the years, we have used this liquid microjet mixing technology to generate neutral dissolved carbon dioxide, carbonic acid, bicarbonate, and carbonate with X-ray spectroscopy at the Berkeley Advanced Light Source, and lots of details here on the electronic structure, the hydration structure, et cetera, of these very important species. But these are bulk measurements. This is not the surface yet. Okay, but we needed to do this on the bulk before we could move to the surface. So we've understood a lot here. Now we want to go to interfacial carbonates. So once again, we use this mixing technology with X-ray photoelectron spectroscopy at the Berkeley Advanced Light Source. This was done by my student Roy Slam, who's now making a whole lot of money with Intel. And he tells me they're not interested in high-priced consultants like me, but whatever. and Hendrik Bloom was at Berkeley at the time, and they worked together on this project. Hendrik has since moved to Berlin. So here, I'm not going to go into any detail with the data here, but X-ray photoemission spectroscopy is what we call a near-surface probe. By tuning the electron kinetic energy that you shine X-rays on your sample and electrons come out, and by tuning the kinetic energy of the outgoing electrons with it, you vary the probe depth, and the shallowest you can probe is 5 nanometers with this. So this is what we call a near-surface probe, and in that near-surface region, we found this very, very surprising result that I'm not going to go through all these data, but this shows, this is sodium carbonate. This is sodium bicarbonate and carbonate. This is carbonic acid and sodium bicarbonate. But I'll just skip to the details. We found that X-ray photoelectron spectroscopy probing this near-surface region of 50-50 mixtures shows that there's much more carbonic acid and carbonate present at the interface than there is bicarbonate. And this is shocking to anybody who's read the classic theories of the behavior of ions at the surface of water. The simple theories, so-called Onsager-Samaras theory, that go back a long time and on which many ideas were based, is totally incorrect. It says there are no ions present at the air-water interface of the oceans. They're pushed away by so-called image charge repulsion. And certainly there would not be multiply charged ions present because the electrostatic interactions between the ion at the surface and its image in the air, we skip all the details, I would say you could never have multiply charged ions. You're not even supposed to have monovalent ions. My group has studied quite a few monovalent ions at the surface of water, and working with theoreticians like my good friend, the late Phil Geisler, we've established the mechanism by which these monovalent ions go to the interface, which they weren't supposed to do. That's beautiful work from Phil Geisler's group on the mechanism of this. But multiply charged ions should never be present at the surface. So that work was published 7 years ago or something like that. Since then, we developed some more new tools very recently to address this again in more detail. The X-ray stuff probed the near surface region, 5 nanometers deep, whereas these nonlinear optical laser techniques probe the outermost liquid layer, one layer. So you get real detailed surface information. And what we found from these results done by my student Shane Devlin, we confirmed this reversed fractionation. There's, again, more doubly charged carbonate at the air-water interface than there is singly charged bicarbonate. And with these techniques, we were able to extract the Gibbs free energy of adsorption. This is the force that controls the behavior of ions as they try to move toward the surface. And look, the numbers are surprising. The carbonate, the doubly charged ion, has a Gibbs free energy of adsorption to the surface of minus 11 kilojoules per mole, whereas the singly charged bicarbonate is 10 times less. This is shocking. This is truly shocking. If you believe me. If you don't believe me, I'll sing. So anyway, these are the data that show this doubly charged carbonate shows much stronger adsorption to the interface than does the singly charged bicarbonate. So what do you do when you get these results? You go find some excellent theoreticians to model this for you. And in this case, this is Shane Devlin, who did the experiments and is about to be a postdoc. And we have been collaborating with Todd Pascal at San Diego, who is a simulations modeler and really wonderful theoretician. And These are the results that Todd Pascal came up with. He agrees in his simulation, he also finds carbonate agglomeration, that the carbonate is indeed strongly present at the interface, much stronger than the singly charged bicarbonate. And his reasoning is agglomeration is happening at the interface. It's not just a bare carbonate ion. The carbonate ion is pairing with its counter ion that's present in the solution, namely sodium or potassium. It's forming an ion pair, and it also is attracting the proton. So these multiply charged ions appear to exert very strong electrostatic attraction for ions of the opposite charge, protons and potassium and sodium in the solution. They form agglomerates. And that's the reason why our experiments are showing so much of the doubly charged carbonate in the interfacial region. We have published a paper on this very recently in the archive, should you be interested in this. And here's the crucial thing. This Todd's calculations repeat this counterintuitive behavior, and he examined this with several different water models, which is important. And these results are apparently holding up to that kind of scrutiny. These findings not only advance our fundamental understanding of ion adsorption chemistry, but will also impact important practical processes such as ocean acidification, sea spray aerosol chemistry, and the mammalian respiration physiology, all this in the carbon cycle. Here's a picture of the carbonates agglomerate that Todd Pascal finds. There are protons sticking on this thing. Again, the key issue is the strong electrostatic attraction provided by these multiply charged ions. So this is the only case that this has ever been seen for. What we want to do in the very near future is extend this to other multiply charged ions that are of primary interest in physiology and geology, like sulfate is our next candidate. Anyway, that's what the agglomerate looks like. So stay tuned. I think when Todd publishes these results, it's going to create a stir. The preliminary paper is available on the web on archive. So that's all I have to tell you about. Thank you. Thank you very much. I greatly appreciate the invitation, even though you invited me because of a false rumor that I can sing. But Charlie and Alex solved that problem for us. So thank you very much. I'm really honored that you invited me here.
So thank you so much. That was a wonderful presentation and an inspiring performance. And I actually heard word around the world that some people joined in singing at home. So.
All right.
But while we're testing the next computer, we actually have a few minutes to take some questions. There will be a question and answer period during the panel session, but we'll take a couple questions now. So go ahead. If you don't mind going to the mic. Well, you're there, so why don't you start?
Rich, you know that the old controversy that's been around for a long time of that water air interface is negatively charged, where all the earlier work, yours and others, suggested positive. So have you laid this old argument to rest with these new results?
Clayton is, of course, an expert in water surface chemistry and so on. This is another poignant controversy in the water business. What is the pH of the liquid water surface, right? This is what you're saying? Some people conclude from excellent experiments in theory that the surface is charged negatively by hydroxide, and you're going to hear more about that. very soon from Professor Zaire. Another group of people conclude that the surface of water is positively charged because of protons. My group currently stands with the positive that the pH of the liquid water surface is somewhat acidic. That's what our experiments tell us. And that's, as experimentalists, that's all we have.
Yes, but the bicarbonate is always there.
Oh, but I was talking about pure water.
Yeah, well, is there such a thing?
There is no, very good point.
In the environment.
There is no such thing as pure water. You always have to keep that in mind. It'll have some memory of the container that it was in, or if it's exposed to air for a very short time, that's exactly right. You always have to recognize that when you're doing experiments on water. No such thing as pure water. And another fact that has been revealed to us is that when you have water moving in a container, in a tube, or anything else, its physics is very different than when it's stationary.
Well, we have time for a couple more questions, but before we hear our next question, I just want you to know we had an online question asking for a repeat performance of the music. We don't have time for that today, but we'll go with the next question, please.
Oh, on that subject, are we going to have a sing-along after dinner tonight?
Feel free.
Well, somebody told me they were recruiting us to do that.
Okay.
If we are going to do that, if the faculty club allows that, which is debatable, would our students come?
Well, we'll have to keep them posted online.
Okay,
Okay, but you are allowed to sing at the faculty club.
okay.
Okay, go ahead.
Yeah, my question regards you were doing the second harmonic generation with a water and air interface. What would happen if you were having a bicarbonate buffer, but you don't actually have 420 ppm of CO2 above the surface, but let's just say you have something more, something less, or no CO2 at all? Does that change exactly what is going to be forming at the surface?
Yeah, I don't know how to answer that question. The nature of the surface is very different than the nature of the bulk. So I don't know how to answer. Those things are just now being investigated in detail. There's a very important finding, theoretically, not from my group. I think who did. Oh, this is an older paper by my late colleague David Chandler. I believe Willard and Chandler wrote this paper some time ago. That it's called the instantaneous interface picture of the water, air-water surface, let's say, and it shows that it's very layered, and there are layers of water that have different structure in the layers, and there's spacing between the layers, and that has a profound impact on surface chemistry that's only now just being understood. Again, the older experiments and older thinking on the water surface embodied this critical concept called the Gibbs dividing surface as the definition of the interface between air and water, let's say. And that's used in the old literature all the time. But it's very deep. The Gibbs dividing surface is much too deep to reflect the actual surface chemistry, and it's just now being revised because of the Willard-Chandler theory, et cetera.
So no studies have been done varying the atmosphere above the surface of the water?
Not in a real controllable way yet. It's just starting. The stuff I showed you is new. It's just starting. There are several groups in the world who are doing excellent experiments on this kind of thing. So stay tuned.
Okay, thank you.
Thank you. So we'll take one more question. Shuguang, go ahead.
I'm always wondered, and the planet Earth has roughly 70% of water on the surface, and the human body, animals, also roughly 70% of water. Is this a coincidence of nature?
Well,
Like 5 years old question.
I am a humble chemist, not a philosopher, but life did supposedly emerge from the oceans. So it really wouldn't be too surprising if cells had a very similar composition to the ocean itself, right? That's a profound question that remains to be answered by the professional biologies, right?
Okay, well, thank you. That was a wonderful presentation. We greatly
Thank you.
appreciate it.